We're surrounded by randomness every single day. The weather, the stock market, even just your commute to work. But what if I told you we have a powerful set of tools designed specifically to make sense of all that chance? Well, today we're going to dive into the world of discrete probability distributions and show you how to find the patterns hidden inside all that uncertainty.
So, let's start with a question. What do defective mobile phones, a baseball player's stats, and winning the lottery all have in common? I know, at first glance, they seem completely unrelated, right? One's about manufacturing, another is about sports, and the last one, well, that's just pure luck. But believe it or not, there's a fascinating statistical thread that ties them all together.
And the answer is they can all be understood and even modeled using the power of probability distributions. Now, what are those? Think of them as frameworks, or maybe like blueprints for making sense of chance. They let us calculate the likelihood of certain things happening, turning all that random noise into something we can actually analyze and maybe even predict.
To build up our statistical toolbox, we have to start with the most fundamental piece, the absolute basic building block. And that's called the Bernoulli trial. You can think of it as the single atom from which everything else is constructed.
And that's it. It's super simple. A Bernoulli trial is just any random event that can only go one of two ways. It's a yes or a no, an on or an off, a heads or a tails. This simple binary nature, two outcomes, and only two, is the core idea we're going to build on.
Now, here's what's really interesting and kind of tricky about how we define success. It doesn't actually have to be a good thing. Look at the manufacturing example. A defective phone is what we're calling a success. Why? Because it's the specific outcome we've decided to count. So success is just a label for the event we're interested in, whether it's good or bad.
Okay, so a single coin flip is a Bernoulli trial. But what happens when we do it over and over and over again? Well, that's where our first major tool comes in, the binomial distribution.
The binomial distribution was designed to answer exactly this question. We're not looking at just one coin flip anymore. Now we're looking at, say, 10 flips or 100. We're not just checking one part off the assembly line, we're inspecting an entire batch.
Now, for the binomial distribution to work its magic, these four conditions have to be met. First, you need a fixed number of trials. You decide beforehand you're flipping the coin 10 times. Second, each trial has to be a simple success or failure. Third, the probability of success can't change from one trial to the next. And finally, the trials have to be independent. The outcome of one coin flip can't affect the next one.
This right here is a perfect example of the binomial distribution's power. It's a classic binomial problem. We have a fixed number of trials, 3 phones. Each one has 2 outcomes, defective or not. We assume the probability of a defect is constant, and the phones are independent. This is exactly the kind of question this tool helps us solve.
Okay, so let's switch gears a bit. We're going to take those same building blocks, those simple Bernoulli trials, but we're going to ask a completely different kind of question. We're shifting our focus from counting successes to waiting for one.
The key word here is first. Seriously, everything hinges on that one word. We're no longer asking how many successes did we get. Now we're asking how long until we get our very first one. This is a model for patience, really. How many times do I have to roll a die to finally get a 6? Or how many calls do I have to make to get my first sale? This slide nails the crucial difference between the two. With binomial, the number of trials is fixed, and we count up the successes. With geometric, the number of successes is fixed, we're stopping at exactly 1, and we count up the trials it took to get there. Getting this distinction right is the key to knowing which tool to pull out of your toolbox.
And here's a perfect real-world example. Imagine you're on a quality control line. You keep testing light bulbs. The test itself is the trial, and let's say our success is finding a defective bulb. You keep counting how many good bulbs you test until you find that first faulty one. That's a classic geometric scenario.
So, the tools we've covered are incredibly powerful, for sure. But our statistical toolbox has even more specialized instruments for different kinds of problems. Let's take a quick peek at a couple more.
The Poisson distribution is fantastic for modeling rates, how many times something happens over a period of time or in a specific area. Think about the number of emails you get in an hour, or the number of typos on a single page of a book. It's all about events happening in a continuous interval. And the negative binomial? It's like a superpowered geometric distribution. Instead of waiting for just the first success, you're waiting for a specific number of them, the second, the third, or even the 10th success. So if geometric asks how long until 1, Negative binomial asks, how long until we get R of them?
All right, so after that quick tour, let's zoom out and get everything organized. The goal here isn't just to know these distributions exist, but to know which one to reach for and when.
Think of this table as your cheat sheet. It really boils everything down to the core question each distribution answers. Bernoulli is for one single event, yes or no. Binomial counts successes in a fixed number of trials. Geometric counts how many trials it takes to get that first success. And Poisson counts how many events pop up over an interval. It's that simple.
And this is really the whole point. These aren't just abstract formulas in a textbook. They are powerful frameworks. They give us a language and a structure to talk about randomness, helping us move away from just guessing and toward making informed, data-driven predictions about the world around us.
So think about it. The number of green lights you hit on your way to work. The number of customers who walk into a coffee shop in an hour. The number of times your favorite song plays on the radio. These things might not be as random as you think. Now you have the tools to start looking for the patterns. What will you find?